It's recording, so we are live on YouTube as well. I mean, not live on YouTube, but this will be uploaded on YouTube. So welcome again, and apologies for the delay. It's one of those things. So I actually forgot, because we are running late. I forgot to put the agenda, but we'll just continue with some facts. I will throw a lot of facts about cycles, so you can go and think about it. And some challenges here and there. And we finished wrapping up about the cycles in the next session. I wanted to do it today, but obviously I didn't have time. And also I think it's better to split the remaining stuff in two sessions instead of, because there's a lot. You will see it will be a lot of, might be a bit challenging for some of you. For those of you who have seen this before, it's probably not. So anyway, because I know we have new people joining, so this is where we are. We are in lecture 12 of 20. I think it will now happen 20. Let's see how we get on to matrix group section. I want to make it as natural as possible, the transition from what we have been going through with actions and all these things, and a bit of a flavor of a representation theory as well, because this is something that you will do in the Lee group session. So we are here in the crash course. So the next jump will be on a sequel of this, will be Lee groups and representation theory, for those who are interested in these things. Before that, we had a course on topology and differential geometry. The reason for that is exactly because of Lie groups, because, again, I keep repeating every week, Lie groups are not just algebraic structure, they're smooth manifolds. So in order to really understand what's going on when you deal with them, you need to understand not just the algebraic side of things, but also the geometry. So that's why we did it. And in the grand scheme of things, we actually didn't start with the group theory. We started with the sets, binary operations and set, and then we went to semi-groups quickly. We went to monoids, and we are here in groups. And we've been focusing on special type of abstract groups, like cyclic groups. And then we did a talk on the application of cyclic groups in cryptography. In this case, it was the Diffie-Hellman key exchange. And then at the moment, we are in symmetric groups, permutation groups. And the idea is we will eventually get to matrix groups, which the end of the technical crash course, we'll learn few things about them, just to give you some head start when you get to Lie groups. Because these matrix groups, especially these guys highlighted here, the orthogonal group, the special orthogonal group for the real case, and the unitary group and special unitary group, these are actually the important, the prototypes of Lie groups. So by being familiar with them already in the abstract sense, it makes it easier for you once you transition into the Lie group stuff, when we are taking into consideration the geometry. So that's where we are. Before we start, I just want to say we have a Q&A session coming up on the 20th. So that's next week on a Saturday, I believe. It's 4 p.m. BST, British Summer Time, and 11 a.m. Eastern Time, with myself and James. So this will be a Q&A session about a course on measure theory and functional analysis, which will start at the end of this month, in August the 29th. So it's an opportunity for those of you who want to take this course to just come in and ask some questions, to myself and James. And the interesting thing about this course is the format will be a little bit, radically different from what we've been doing so far. Instead of these bi-weekly sessions, and sometimes obviously we skip it because of my availability, there will be like a pre-recorded sessions by James with homework assignments and these things, and then there will be like a study groups with James, discussion and study session with James himself, and then we will publish the homework solutions at the end, and so on. So it will be more of a hands-holding thing for you, because this is a little bit more harder, and also because James has more time than me. So it will be, it's a trial format. If it goes well, maybe we will, transition to this. Which means, sadly, if we transition to this, obviously I have very limited time. I won't be able to be recording and uploading stuff and these things. So I'll have to bring someone else. But rest assured that I will not go away. I will be doing some guest appearances, especially on the applied side. When they teach you the maths, I come in and show you how it's being used and these things. And in the eventuality of some of them, for some reason they cannot continue, maybe that will show up, and then we'll continue with we'll resume the format that we've been doing. So I'll be on the sidelines, but yeah. Okay. Enough of blah blah blah. So does anyone have any questions so far about the number of sessions and these things? We'll finish on the thing right before the hour, because I don't have much to go through. Just few facts about cycles, and then we wrap it up today. Is there any question about what's coming up? I mean, about this functional analysis of measure theory, we will share more about the structure and all this, the motivation and what's coming up after it. Things like operator algebras, non-commutative geometry, all this stuff. Okay. So before we start, how is everyone in terms of the cycle notation and these things? How was the last study session, George? Did you have some people?
It was just me and Bob and Dimitri for a little while.
All right.
Bob did the bulk of the work.
Okay.
I got to confess that the cycle notation is one of the things that confused me years ago. And I confess I got confused between the permutations and the set they're acting on. So the counting is different.
Mm-hmm.
Bob Miller set me straight.
Okay. That's good to know. And everyone else, I mean, it's one of those things that you just have to, go back to it again and maybe check other references.
Yeah.
And these things, I just thought it was very much easier to start with abstract definition of the thing and then go through the actual, notation itself. What a cycle means, what a K-cycle is, because normally in textbooks or what I've seen people do, they start with plenty of examples, and a lot of sometimes examples come with the chassis and distractions that you actually lose the essence. So that's why I started with the abstract definition of what a K-cycle is, and then transition to the cycle notation. Okay, so let's crack on. And there will be typos and possibly errors, and it's a good thing if you spot them, because I was in a rush on the train doing things and also in here. So I will be throwing several things about cycles in here. You can double check this with me later. The first thing is that one cycle corresponds to the identity for anything, any A. Okay. In fact, this is why in textbooks, when you have like in the composition of cycles, for example, when one cycles appear, you just ignore them because it's just identity. Okay. The second thing I want to highlight is two cycle, which has another name. Can you see the pointer, by the way? No.
No.
Okay. Sorry for that. So the second cycle, also known as the second cycle, a two cycle, also known as transposition, corresponds to a permutation, a unique one in the permutation group, which switches A1 with A2, but leaves all the other elements unchanged. This also means, as a consequence of this, that the cycle A1 A2 is the same as A2 A1. So they correspond to the same thing. So double check on this. You should be able to see this. Imagine me and George, sitting in two chairs, and we decide to swap chairs. What matters is the end results. Not where we start, whether George came first or the second. I don't know if this analogy works, but it's it's not how we do it. The thing is how it ends. You know, we all end up switched anyway. So so this thing is the same thing. This now for k greater or equals to 3, this is not the case. For example, look, consider this 3 cycle 1, 2, 3, and 3. Sorry, 1, 2, 3, and 1, 3, 2. So let's again in the cycle notation. This means that 1 goes to 2, and then 2 goes to 3, and then 3 comes back again to 1. Okay. And then we have here 1 goes to 3, 3 goes to 2, and 2 comes back to 1. So these are different. Can you see that these 2 cycles are different? You know, because, you know, 1 goes in the first cycle. In this one, for example, you know, 1 goes to 3, but in this one, 1 goes to 2. So they cannot be the same map. Yeah, they are different. Yeah. Yeah, so I hope you can see this. Now, a natural or curiosity question. I hope I spelled curiosity right. George, you are the linguist. It's so embarrassing. The thing that's because in these slides you don't have something like Grammarly and these things, and also, frankly, it's like the time. So I rely on George to correct me. So this question. Is there any way? So you've seen that for k greater or equals to 3, a slight change of the order can change the thing, the actual permutation. The question is, if you are giving a k cycle, A1, A2, blah, 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 to AK, is there a way of making small changes to this, to the order of these elements, to the way how they are positioned, so that the underlying permutation stays the same? Okay. So we see we see a way. So that's yeah. Okay. So we see a lot of people with a lot of ways. So let's see. Here's this proposition I challenge you with. I'm going to call it proposition 1. For those of you joining, you know, we say actually this is a theorem, you know, but you know, in textbooks in mathematics, sometimes, you know, because you're instead of risking having theorem all over the place, you know, you just use proposition for things that are also theorem, but you don't want to highlight them. They are not that well, they are important, but you know, they are less important than the ones that the stuff that you call theorems. Okay, so you will see me name something else theorem that I think it's important. Obviously, this varies, depends on the person. Okay, so this says this proposition: if you have a k cycle, okay, then we have these identities. So the k cycle equals to this, you know, to like for example, putting them in the opposite order, you know, starting with the A2, A3, blah 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 blah, AK, and putting A1 at last, and so on. I challenge you to try this, to try to see this, not in the abstract if you are struggling in general case, but say for example, start with the S3, for example, you know. Start with a simple case, you know, go with the S4, pick a cycle, and try to do this. You will see that they will be the same thing. And another thing is the inverse of a k cycle is interestingly this is just you know, the reverse. You know, you start with the AK and then AK minus 1, blah 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 blah. AK. I hope I didn't make any typos. Or if there is, you should be able to correct me if you try, once you try the use cases. Yeah. So so that means cycles have obviously the inverse is just reversing the order. Okay. So this is essentially what this is telling us, is that we can start a cycle at any point, you know, at any index AI, at any index I. All we need to do is then after that, you know, what comes in is to have like you know, the next element in the index, A plus 1. Sorry, AI plus 1. I plus 1. That's the thing. It's pity I don't have the cursor. Okay, and once we get to the AK, which is the last element, the thing of the index of the k, then that means that the cycle goes back to 1. That's all you have to make sure in order to, you know, you can start the cycle at any position, really. This is where the confusion comes. Yeah.
So only the 2 cycle would be its own inverse.
That's a good question. What do you think? Can you generalize this? I'll leave it to the actual discussion for the study group to see if other people. Yeah, but maybe in the next few slides, some stuff will come in. Maybe they will give you a clue. I hope. If not on this session, in the next session, it's very interesting question. Yes. Yeah. So this. Yeah. So it means the inverse. Yeah. There you go. Yes. And then you have the thing. I'm like my screen is freezing. That's why I'm a bit. Can you see the screen properly?
I see it okay when I go to full screen.
Okay. Yeah. So anyway, so have a look at this. In particular, pay attention to the toe cycle. The inverse of it. There's a name, technical name for this. When the inverse, the thing. I think we talk about the order of elements in the past few sessions or something. This means 2 cycles are of order. I'll leave it to you to try to remember. Order 2. Okay. Another thing, a very beautiful fact about cycles is this: when you have 2 cycles that are disjoint. Remember, disjoint cycles means that their element, they cannot have overlapping elements. Okay, so in this case, it means that AK and AKs, the AKs and BJs are different for all K and J. Okay, so their product, I'm bothering to write, not confuse the cycle notation with the actual product. I'm bothering to write this circle. This is the composition of map product. So when you have this 2 disjoint cycles, their product is commutative. Okay, so 2 cycles, 2 disjoint cycles commute with each other. Okay. Now I have this. I want to answer this. I'll leave this as a challenge for the study group, but I think some of you will already see it's like the thing. What if the cycles are non-disjoint? Does it follow necessarily that they don't commute with each other? I'll leave this. Maybe you can find a counter example or something, but it's one of the challenges. Another beautiful thing about cycles is this proposition 1.2. So I have a lot of proposition. Is that given a permutation, sigma, arbitrary, this doesn't necessarily need to be a K cycle. Okay, this is another arbitrary permutation. Okay, and given a K cycle, we have this beautiful identity. So this composition between sigma, the K cycle, and the inverse of sigma yields this. This is very beautiful. Now the question is, if this guy, if this is also again a K cycle, this is a challenge for you to think. You can, again, you don't have to, if this is might be a little bit, how do you say, boring or, labor intensive to try to prove this in generality, but try at least with the small n, just with the concrete example, with the, say, S3, for example, okay? S3, not S3 Amazon bucket to the developers. This is a symmetric group. I know we have developers on the audience.
Mathematicians were using S3 long before Amazon.
Before Amazon, yeah, before. That's true, yeah.
We should get a little commission.
Yeah, that's true. Okay, so I leave this as a challenge. but it's really important for you to go and try to see this for yourself. Start with like an example, a toy stuff with, say, start with S3, for example. S3 is a good starting point because you'll be able to see this more. Let's see. More facts, I hope. No more facts. So we have this. We'll talk now about even and odd permutations. But before that, I will present this very beautiful. This is a theorem. I've decided to label it a theorem. Yeah, so Barry is saying sue Amazon for trademark infringement. Yeah. Yeah, that's because I had a call with mathematicians. We are talking about Amazon S3, and one of them was confused what S3 I was talking about. I was like, it's not the symmetric group S3. We are talking about the bucket. Yeah, so this beautiful theorem, it says, given a sigma, an arbitrary permutation, again, it doesn't need to be a K-cycle. It doesn't need to be a cycle. This theorem says that this can be written as a product of two cycles. This is very beautiful. So that means any permutations in SN can actually be decomposed as a product of cycles. How many products? That depends. We'll come to this at some point, I guess, in the next sessions. But for now, for example, you can see, for example, for K cycle, we have this decomposition here. You can actually also try to see this with the simple use case instead of trying to prove this in abstract. Start with, say, S3 again, and then you will see a 3-cycle. A cycle on S3, a K cycle on S3 will have this decomposition. Now, this brings me to this very important definition, this thing of, when is a permutation odd or even, okay? So we say a permutation sigma is even if it can be written as a product of an even number of 2 cycles, okay? So if that's the case, then we say it's an even permutation. Otherwise, if it can be written as a product of odd number of 2 cycles, then we say it's an odd permutation. Okay. So once you break down, you find out, you decompose a permutation into cycles. You know how many 2 cycles you have decomposed that, and then you will know whether that permutation is odd or even. This actually, to help you with that, we have this other beautiful theorem which says, giving a permutation sigma, sigma is either even or odd, not both. So it cannot be. You cannot have a permutation that is both even and odd. So there can only be one of them. So a permutation is either odd or even. Okay. And then this brings me to the next thing. This theorem. I hope you can actually try to see this with, say, for example, with some concrete examples. Hopefully, you can see this. A K cycle is an even permutation if K is odd, and odd permutation if K is even. Do you agree with this? You can see this, okay? And then I have these curious questions for you: is what is the identity then? Looking at this, if this theorem is true, you can try to prove it or disprove it. Does anyone agree this theorem is true? Well, otherwise I wouldn't write it, or have I made a mistake? Okay, this is something for you to go and think about. But I mean, if you come through several examples, you should probably see that it's true. Yeah. So a K cycle is an even permutation if K is odd, and odd if K is even. So it switches. Okay. And then the question is the identity even or odd? Depending on what is the identity. Is identity, what K is identity? What sort of cycle is it? And then it will tell you the thing. Are two cycles even or odd permutations? I think it's right on the face, right? Yeah. So if you are struggling to answer this, please go review again. We will not be mad at you. It's okay. That's fine. But just go in the review. So this is very, very, very beautiful, isn't it? And then it brings me to another thing. This is where we start to transition to the next definition, which is the sign of a permutation. This is something else, something we need for something in the next session. We'll continue with this. So given a permutation sigma, an arbitrary permutation, okay? It doesn't matter which, whether it's, it doesn't need to be a cycle. The sign of sigma is defined as follow, okay? Sigma of, sorry. The sign of sigma is defined as well. Sign of sigma equals +1 if sigma is even in the sense of the definition that we just given, whether it can be decomposed as a product of an even number of two cycles. Okay, so it's +1 if sigma is an even permutation, -1 if sigma is odd permutation. Okay, we normally, in some tests, we normally don't like plus and all this, but because we are talking about sign, I thought it's just easy to do it this way. But normally in test books you omit it because just like 1 is positive, you don't always write +1, right? But I just put it just to make it obvious. And then this is very, very interesting thing. I hope you can see this. This is like, I think, the first session of group or the second theory session or something where we talk about homomorphisms. Okay, so this sign of a permutation, it goes from the symmetric group Sn to this group. This is under a multiplication. This is a multiplicative group, right? You can see this. This is a group, right? So this is a homomorphism, meaning that it has this property. Sign of sigma 1 composition with sigma 2 is the same as this product for all sigma 1, sigma 2 in the permutation. Now, these are very interesting. You also learn that the notion of kernel. When we talk about homomorphism. So in this case, the kernel of this homomorphism is essentially, this is the definition. By definition, is a set of all permutations in Sn whose image equals to 1, because 1 is the identity of this multiplicative group, right? So this is non-trivial. This is essentially another way to say this. This is the set of all even permutations, right? Because 1, the only thing is the only way it gives 1 is if the permutation is even. So that's the set of all even permutations. And this has a very interesting name. It's called it's a subgroup, obviously. This is a subgroup of Sn, and this is called alternating group. Okay, this is a very, very important group in mathematics. We'll come to this in the next session. And this is it. We don't have much to cover today, that's why, but we will finish wrapping up the rest. The rest of there will be some other results that I will share, instead of going through all everything, and then we will start with the group actions and so on. We'll also define notions like orbit, for instance, and so on. So that's it. So go and practice. I know we haven't covered that much, but the stuff, the challenges and the stuff that we covered is very important that you go through it. So yeah, that's why I was saying we'll finish on the hour. Before the hour. Yeah. So is there any question?
No. All quiet on the chat.
Okay. Well, it's a little bit of a slow journey, but hopefully I'm going to steer you towards what really matters and these things. And Bob, we are getting closer to orbits and all the other stuff that you need after we go through them, and then you can give your talk. We are getting closer.
My only comment would be, although it's not many topics, each one is very rich.
Yeah. Obviously, we cannot dive in anything in all of it. It's like a massive thing. This is why, if you wanted to go through all this, you should probably dive, extra reading and these things. But each of them is very, very nice, very, very, very thing. This and it has like connections with other. For example, this alternating group. I think I will comment on it in the next session about the relationship with Galois theory, for instance. The thing of solving the ability to whether you could solve a polynomial equation with the radicals or not, for instance.
And also this little piece you showed where you take, I can't remember your notation, but say G and H being two elements, you take G minus 1 H G. That's a very important operation.
Yeah. That's why it's important for you to show up in the study sessions, talk to Joe and review, because a lot of the properties that we have already covered, for example, in next session, when we are covering the orbits over this, the thing will, make use of, the group exponentiation, something that we already covered, So it's very important to remember, some of the key fundamental properties that we went through with.
And I think we have all of the tools in place now to completely decompose the symmetric group into its pieces.
Yeah. Another thing I didn't mention here, we'll do it. I didn't want to do it to not confuse you. That's why I focused today on, on the thing of decomposition by two cycles. But actually, any permutation can be in general can be decomposed as product of disjoint cycles. We'll come to this in the next session. Yeah. So that's it. I know we started late and we are finishing earlier, so this is good. Does anyone have any question or want to make any comment?
20 minutes more time to study.
Yeah, exactly. Yeah, so you can go away and the thing. So you're still doing the study sessions, George?
Yes, as long as that time slot is available and the crowdcast.
Yeah,
yes.
Of course. I will create a crowdcast. Yeah.
I have one suggestion to crowdcast.
Mm-hmm.
A feature recommendation.
Okay, bye, Barry. Yeah. Yes. Sorry.
Okay, bye, Barry. My feature request is that when you're in full screen mode, some kind of little light or button or whatever would light up when there is something new in the chat.
Yeah, I gave them this feedback because even for me, when I go full time, I don't know when there's some question, at least a notification or like visual notification is actually ideal because then you can see something pops up. I mean, I don't know how the thing. I don't think this is hard thing for them to implement really.
No, it's just, I guess, just finding the right place on the screen. Yeah. I won't name them, but it's more than one other video conferencing thing gives you a number that increments when there's unread things in the chat or new things in the chat.
Mm-hmm. 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 I mean, that being like some of my feature requests have been actually implemented. Like one thing I wanted initially in this version, you couldn't duplicate the events because most of the times the events are the same. You just change a few things and this thing, and then before you have to do it all over again. So I was like, can you please allow me to copy the events, and then they did it. Yeah. Yeah. So let me just go here. Now that we have, for those who can stay for a few minutes. Yeah. So this is available on